Hello, my dear students. I'm Shrikala from the Department of Mechanical Engineering, Global Academy of Technology. Today, in this lecture, I'm going to discuss about steam nozzles. Before getting into the details of the steam nozzles, let's see where these steam nozzles are used and its usage. In the steam turbines, boilers will be used to heat the water. The high pressure, low velocity of steam which is coming out of the boiler enters the turbine through this nozzle. This nozzle converts the high pressure steam into low pressure, thereby increasing the kinetic energy of the steam which is coming out of the nozzle. Here also we can see this is a steam turbine blade, and from the nozzle the steam coming out with high velocity and impinging over the turbine so that the turbine will rotate and generate electricity. Now, before getting into in detail of steam nozzle, let's see about the nozzle. Nozzle is a pipe of varying cross section, and it is designed to increase or decrease the velocity of the fluid flowing through it. These nozzles are frequently used to control the rate of the flow, speed, direction, mass, shape, also the pressure which emerges out of it. Normally, these nozzles will be of three types. One is the convergent, convergent and divergent. In convergent nozzle, the cross-sectional area reduces along its length, whereas in divergent nozzle or the diffuser, the area from entry to the exit increases. In convergent divergent nozzle, initially the area reduces to minimum and then it increases. And the minimum area is known as throat. Now let's get into the steam nozzle. The steam nozzle is a passage of varying cross section, and here the part of the enthalpy of the steam, that is heat energy of the steam, will be converted into the kinetic energy as the steam expands from high pressure to low pressure. This amount of expansion depends on the type of the expansion as well as the pressure ratio. Also, these nozzles will be shaped such a way that the expansion process is isentropic so that it provides maximum energy conversion. So as I said earlier, these steam nozzles are used in steam turbines to convert high pressure, low velocity steam to low pressure, high velocity jet which is coming out of the nozzle. Also, these steam nozzles are used for cleaning purpose in thermal power plant, steam refrigeration, etc. Mainly, there are two types of steam nozzles. One is the convergent nozzle and other one is the convergent divergent nozzle. In convergent nozzle, the steam flows through the nozzle and its pressure drops by converting into velocity of the steam. So the maximum pressure drop which can occur, or the ratio of exit pressure to inlet pressure, it can go up to 0.58, and this pressure is known as critical pressure ratio. So this can be obtained if it uses this dry saturated steam at the nozzle entry. In convergent divergent nozzle, the pressure ratio will be less than the critical pressure ratio. That means if we need to expand the steam further, then we need to attach another part, a divergent part, and which is of length higher than the convergent region, and the divergent angle should be limited to maximum 7 degree in order to avoid the wall separation. So by using this convergent divergent nozzle, we can have more expansion and we can get higher velocity compared to the convergent nozzle. Now let's get into some details of these nozzles and obtain some expressions regarding the mass flow rate or the discharge through the nozzle, maximum expansion which can occur. So all these derivations, let's see here. Now for that, let us consider a convergent nozzle, and steady state expansion occurs in this nozzle from 1, that is inlet section of the nozzle, to 2, that is exit section of a convergent nozzle. Let P1 and P2 be the inlet and exit pressures. Capital V1 and capital V2 be the velocities. Small v1 and small v2 be the specific volume of the steam entering and exiting the nozzle. And H1 and H2 be its enthalpies. Let A1, A2 be the area of cross section at the inlet and exit. Now, applying the steady flow energy equation for unit mass flow between inlet and the exit, which we have already studied in basic thermodynamics. So it will be Q, that is heat, plus H1 enthalpy, plus V1 square by 2, that is kinetic velocity, kinetic energy, and Z1G potential energy. That will be equal to W plus H2 plus exit kinetic energy V2 square by 2 plus Z2G. Since we are taking unit mass, so whole thing we are using it for per kg of the steam. Also, through a nozzle, heat transfer Q will be 0 and W will be 0. Also, if the nozzle is straight, we will consider the potential energy also difference be 0. So if we substitute, we will get it as H1 plus V1 square by 2 will be equal to H2 plus V2 square by 2. So therefore, if we simplify, we'll get V2 will be equal to square root of V1 square plus 2 into H1 minus H2. If we neglect the inlet velocity, then we'll get V2 as square root of 2 times H1 minus H2. Here, in this expression, H1 and H2 should be in joules per kg. That means normally the H values or the enthalpy values we obtain from the steam tables will be in kilojoules per kg. So we have to multiply by 10 power of 3 in order to get the velocity here. Otherwise, if we want to substitute H1 and H2, so you'll get it as root 2000 if it is simplified, we will get it as 44.72 square root of H1 minus H2, where H1 and H2 will be in kilojoules per kg. Normally, there will be frictional losses which occurs, or there will be friction between the steam and the wall of the turbine, and that losses will occur between 10 to 15%. So this increases the enthalpy at the exit by 10 to 15%, or enthalpy drop will be reduced by 10 to 15%. So then the velocity at the exit will be equal to 44.72 square root of K. K is nothing but the frictional losses into HD. HD is nothing but the drop in the enthalpy. So this much reduction will be there, where K is in the frictional loss factor and HD is the drop in the enthalpy through the nozzle. Now let us obtain the condition for the maximum discharge or the critical pressure ratio. This critical pressure ratio, as we say, is that is 0.58, and that is the maximum pressure ratio which can occur through a nozzle. So we have already studied that. So work done per kg of the steam of flow through a nozzle, and if it is an isentropic, then n by n minus 1 into P1 V1 minus P2 V2. This net loss in the enthalpy should be equal to gain in the kinetic energy of the steam. So V2 square by V2 square by 2 should be equal to n by n minus 1 into P1 V1 minus P2 V2. If we simplify, we'll get it as n by n minus 1. If we take this P1 V1 outside, get 1 minus P2 V2 by P1 V1. But we know for an isentropic process, so P1 V1 power n is equal to P2 V2 power 1 n. Therefore, V2 by V1 will be equal to P1 by P2 whole power 1 by n. Substituting in the above equation, we get V2 square. If we substitute this V2 by V1 here by P1 by P2 power 1 by n, if we substitute, we'll get this expression. So V2 square will be equal to this 2 we are multiplying here. So we'll get as 2n by n minus 1 P1 V1 into 1 minus P2 by P1 retaining as it is, and V2 by V1 replacing it by P1 by P2 power 1 by n. And if we simplify, we'll obtain the expression as V2 equals square root of 2n by n minus 1 P1 V1 into 1 minus P2 by P1 power n minus 1 by n. This is the expression for the velocity at the exit of the nozzle, where this value of n varies between 1.135 to 1.3. And it will be 1.135 for dry steam inlet, that is inlet of the nozzle. If it is dry saturated steam, it can be taken as 1.135, and it will be 1.3 for the superheated steam at the nozzle entry. Now, we know the mass flow rate, and this will be maximum at the throat because throat will be having the minimum area. Hence, mass flow rate per kg of the steam through the throat, and let that throat be having the area of cross section A2 and density ρ2 and velocity V2. So this density unit is kg per meter cube, which can be taken as 1 by V. The V is nothing but the specific volume, and its unit is just 1 by rho, that is nothing but meter cube per kg. So ρ2 I am replacing by 1 by V2 here. So A2, capital V2 is nothing but the velocity here at the throat divided by small v2, the specific volume of the steam at the throat. That will be equal to A2 into this V2 expression as we obtained in the previous slide, substituting here, divided by specific volume. As we said already, P1 V1 per n is equal to P2 V2 per n because it is an isentropic flow. Therefore, V2 will be equal to V1 into P1 by P2 power 1 by n. So, we are substituting this for this denominator V2. So, what we get A2 by A2 square root of 2n by n minus 1 into P1 V1 multiplied by 1 minus P2 by P1 whole power n minus 1 by n divided by, we are substituting this expression for V2. V1 into P1 by P2 power 1 by n. Then if we simplify, we'll get it as A2 by V1 as it is. And this P1 by P2 power 1 by n goes to the numerator, and inside the numerator it becomes P2 by P1 because it becomes a reciprocal when it goes to numerator. And if it enters inside the square root, it becomes P2 by P1 power, instead of 1 by n, it becomes 2 by n. And that will be taken inside. So we are substituting 2n by n minus 1, this P2 by P1 power 2 by n into P1 V1 multiplied by 1 minus P2 by P1 power n minus 1 by n. So and simplify, we'll get it as the mass flow rate, that is at the throat, be equal to A2 by V1 square root of 2n by n minus 1 P1 V1 into P2 by P1 power 2 by n minus P2 by P1 power n plus 1 by n. And this mass flow rate, if we observe, we can see that it depends on the inlet conditions as well as the pressure ratio. It depends on the area of the throat, and it is independent of any other things. So now this expression, as I said, this mainly it's a function of P2 by P1. P2 by P1 is nothing but the pressure ratio. So if for maximum discharge, we are differentiating this mass flow rate with respect to P2 by P1 and equating it to 0. So we'll take only this expression because others are independent of P2 by P1. So n by n minus 1 are constants, and even inlet pressure and inlet specific volume will be constant, area of cross section will be constant. So we are taking only this part P2 by P1 power 2 by n minus P2 by P1 whole power n plus 1 by n, and differentiating that with respect to dP by dP2 by P1 and equating it to 0. So we'll take this part. So this is with respect to, this is similar to d by dx of x power n. So it will be equal to n into x power n minus 1. So that we are substituting here. N is nothing but here 2 by n into x power n minus 1. X is nothing but here p2 by p1 whole power n minus 1 is 2 by n minus 1 minus, again similarly here also n plus 1 by n into p2 by p1 whole power this whole thing minus 1. That should be equal to 0. Now we are taking this part on the right hand side. So you'll get it as 2 by n into p2 by p1 whole power 2 minus 1. If simplify this, you'll get 2 minus n by n. That should be equal to n plus 1 by n into p2 by p1 whole power. This, if we simplify this, n plus 1 minus n. So n cancels, you'll get it as 1 by n. Now here I'm taking this constants on the other side. So 2 by n I'm not retaining as it is. This n plus 1 by n I'm taking on the other side. It becomes n by n plus 1. That should be equal to p2 by p1 whole power 1 by n, retaining as it is, multiply by this. I'm taking it to the denominator. So when it comes to denominator, it becomes p2 by p1 whole power 2 minus n by n in the denominator. When that goes to numerator, so it's similar to a power n by a power m by a power n will be equal to a power m minus 1. Similarly, this a power m by a power n will be equal to a power m minus n. So when 1 minus 1 by n minus of 2 minus n by n, we simplify, we'll get it as n minus 1 by n. So here n cancels. So in the LHS, you'll get 2 by n plus 1 equal to p2 by p1 whole power n minus 1 by n. And finally, we'll get this p2 by p1 will be equal to 2 by n plus 1 power n by n minus 1. So this pressure ratio is known as the critical pressure ratio, and with this pressure ratio the discharge of the steam will be maximum. Through the nozzle will be maximum. So we should remember this critical pressure ratio expression for solving the problems. And this value P2 by P1 will be equal to 0.577 or 0.58. This for dry saturated steam entry at the nozzle. And normally its value N will be equal to 1.135. Now, substituting that above pressure ratio, this pressure ratio 2 by n plus 1 power n by n minus 1 for the m mass flow rate. Here we obtained m value to obtain the maximum discharge. So we'll get it as m dot is equal to a2 by v1 into, so only that p2 by p1 is replaced by 2 by n plus 1 power n by n minus 1 for 2 by n. This is in the mass flow rate, and simplify, we'll get the maximum discharge as m is equal to a2 into square root of n into p1 by v1 into 2 by n plus 1 power n plus 1 by n minus 1. So this is the expression for the maximum discharge. And from this we can see that this mass flow rate equation or the discharge equation is independent of the pressure at the throat, and it depends only on the inlet conditions and independent of the pressure at the throat. Hence, since it is independent of the pressure, so addition of the divergent portion of the nozzle for a convergent nozzle will not affect the mass flow rate of the steam. So now if we substitute this critical pressure ratio in the velocity equation which we obtained in the previous slide, we will get V2 is square root of 2n by n minus 1 P1 V1 into 1 minus P2 by P1 over n minus 1 by n. So if we simplify, we will get maximum velocity as square root of 2 into n by n plus 1 P1 V1. And which shows again the exit velocity of, this is the exit velocity of the steam. It is dependent on the steam entry conditions at the nozzle. Now, let us see the effect of this friction on the steam nozzle. Theoretically, flow through the nozzle will be assumed to be isentropic and neglecting the effects of friction. Theoretically, we assume the flow to be isentropic, but practically there will be the friction occurring between the nozzle and the wall, as well as this friction occurs between the steam and the nozzle surface. It occurs within the steam itself, and also sometimes due to shock. Most of these frictional losses occur in the divergent portion because this divergent length is quite higher compared to the length of the convergent nozzle, and hence it is subjected to more frictional losses. Also, the divergent portion is subjected to higher velocities, and these effect of friction are listed below. First is the effect of friction is expansion is no more isentropic. So let us see the HS diagram here. In this HS diagram, consider the point 1. This point 1 is in the supersaturated region. This line which is showing, this is the dry saturated line. And now let us consider a convergent divergent nozzle. And in the convergent divergent nozzle, 1 to T, this T is nothing but the throat, and 2 is nothing but the at the divergent end of the convergent divergent nozzle. Here we can see the 1 to T is nothing but the expansion of the steam from nozzle entry to throat. Here there will be not having any much losses because it is convergent section is very small. And what it is said is from throat to the nozzle exit at the divergent part, it will not be isentropic in the practical case. It will be of this. That means the enthalpy of the steam coming out of the steam will be higher than the isentropic enthalpy. That means enthalpy when there is no friction. So what happens, there will be frictional heating of the steam occurs since it is steam is dryness fraction and increases the steam dryness fraction. Also sometimes it will superheat the steam and in turn it increases the specific volume of the steam. Also, it reduces the exit velocity of the steam because of the frictional heating of the steam. Now, this effect of steam is taken into account in the nozzle efficiency, and this nozzle efficiency will be equal to actual enthalpy drop by the isentropic enthalpy drop. Here we can see the actual enthalpy drop is from here 1 to 2 dash. H1 to 2 dash is the H1 to H2 is the isentropic enthalpy drop, and H1 to H2 dash is the actual enthalpy drop. So actual enthalpy drop is H1 minus H2 dash divided by isentropic enthalpy drop is H1 minus H2. Also, we define one more expression called the velocity coefficient, and it will be ratio of actual velocity to isentropic velocity, and if we simplify, we obtain it as square root of nozzle efficiency. This nozzle efficiency depends on various factors such as material, size, shape of the nozzle, the Reynolds number, also the divergent angle in the divergent portion, also the fluid nature. So while designing the steam nozzle, there will be two types of complications which occur. One is the loss in the kinetic energy due to frictional heating between the walls and the steam, which reduces the enthalpy drop by 10 to 15%. And one more important phenomena we observe is known as supersaturation. This I'll be explaining in the next slide. Now, this supersaturated flow or a metastable flow through the nozzle. Here, when a dry or superheated steam is expanded through a nozzle, the actual mass flow rate coming out of the nozzle will be greater than the theoretical flow, mainly because of the time lag in the condensation. That means here, let us see here, see the point number 1, which is in the superheated region, and this line is the dry saturated line. Now, when the steam in a superheated steam enters a nozzle, the condensation should occur at this point 2, which is lying on the dry saturated line. But the condensation will not occur at this point 2, but it continues to be in a dry state till this point 3. This is mainly because of the time lag in the condensation because the convergent portion of the nozzle will be too short and the steam velocity will be too high, so that the molecules of this steam will not have sufficient time to form into droplets. So this condensation will not occur at point on the dry saturated line, but it continues to the point somewhere at 3 unnaturally. And this flow of the steam is known as, or this state of the steam is known as supersaturated steam. But the actual condensation will start occur from the point 3 and it continues to be a normal flow. But the region between 2 to 3 will not be in thermal equilibrium, and this region is known as the supersaturated zone, where the condensation is delayed from point 2 to 3, mainly because of the time lag in the condensation, or it's not getting sufficient time to condense. So these points which where the actual condensation occurs is known as the Wilson line. And further after this point, the uh, normal steam state continues. So now the same thing he explained here in the next slide. So this HS diagram is considered. See, process 1 to 2 is isentropic, as I said, and change of phase should start to occur at the point 2 lying on the pressure line. So that is point 2 on the dry saturated line. But in case of the nozzles, due to supersaturated flow, condensation will not occur at point 2 but continues to expand in the dry state until the point 3, and that means the condensation will be suppressed. From the point 2 to 3, condensation will be suppressed. So that state will be known as supersaturated state or the metastable flow. See, the process 2 to 3 shows the expansion and the supersaturation region. As I said, it will not be in thermal equilibrium. So it is also known as undercooling because at any pressure between P2 and P3, the temperature of the vapor will always be less than their saturation temperatures. That means if we consider the saturation temperature at P2 and saturation temperature at P3, the actual temperatures will always be less than these saturation temperatures. And that difference between the actual temperature and the saturation temperature at any pressure is known as degree of cooling. And also, as I said earlier, these locus of the points where the actual condensation takes place is known as Wilson line, and this is independent of the temperature and the pressure at the nozzle entry. And this will be considered as, for all the practical purposes, the line as the saturation line. So as I said, the flow between these two, the actual saturation, theoretical saturation line and the actual saturation line is known as the metastable flow. Also, it is said the ratio of the saturation pressures corresponding to temperatures 2 to 3. That means the temperatures, as I said, it will not be saturated temperature. The temperature will be less than that. So the corresponding saturated pressures at 2 and 3 and its ratio is known as degree of supersaturation. So as I said, at point 3, the limit of supersaturation will be reached and steam condenses in the normal state. So 3 dash to 4 dash is again isentropic. That means where it is in the divergent portion. And it can be seen that 4 and 4 dash lies on the same pressure line. That means 4 and 4 dash. This 4 dash is mainly because of the frictional heating, which increases the enthalpy of the steam. So these two will occur on the same pressure line since the flow of the steam will be natural beyond the point 3. Now at the end we'll see what are the effects of supersaturation. So what it does, it will increase the enthalpy and specific volume of the steam, as we already dealt earlier. There will be slight reduction in the enthalpy during expansion. So correspondingly the steam velocity at the nozzle exit will reduce. And since the steam is undercooled with temperatures which is less than the saturation temperatures, the density of the steam increases. Thus, which, since the density increases, we know mass flow rate M is equal to rho AV. So with the increase in the density, and since density is directly proportional to the mass flow rate, so the actual steam discharge through the nozzle also increases, and that's why it will be higher than the theoretical discharge. Thank you.